This is the last of the longer answer questions from the first set of organic chemistry questions. So part A, draw the displayed or full structural. The reason that both those terms are in there are because some exam boards use the term displayed formula and some use the term full structural. Either way, it means showing all of the bonds that are present in a molecule. So 2-bromopropane, nice and easy. 3 carbons in a row for propane, bromine on the second carbon, doesn't matter whether you're pointing it upwards or downwards, and then don't throw silly marks away by forgetting to include the rest of the hydrogens. So, a sample of 2-bromopropane was mixed with ethanol and an aqueous solution of silver nitrate. Aqueous is important. The mixture was warmed in a water bath, and after a short period of time, a cream precipitate appeared. So this reaction is involving the substitution of the bromine with an OH group, and we're not told that any sodium hydroxide is added, we are only told aqueous solution. So the key thing here is that the reagent that's reacting is water. So I could do it with displayed formula, but it's easier if I just write my balanced equation using molecular formulae or structural formulae. So I'm going to choose structural so I can really see what's going on. I've got CH3, CHBr, CH3. Again, there's no reason you can't do this displayed. And I'm going to react it with water because that's what's present that's reacting in the organic reaction, and I'm going to make CH3CHOH, CH3, so I've made propan-2ol, and then because it's substitution I have another product which is HBr. So balanced equation is only worth 1 mark. There's various ways of doing it. As I said, you can do a displayed formula, you can kind of do a combination of both of them. It's also okay in this instance to do a molecular formula, so you could have done C3H7Br and then C3H7OH on that side, or maybe even C3H8O. That would be quite unusual because you're not really showing the functional group then at all. Name and mechanism is nucleophilic substitution. Substitution is the name of the reaction and the mechanism is nucleophilic because it's a halogenoalkane and that's the only thing they do. So part 1 then, so although we're adding silver nitrate is simply so that we have an observation, because if I were to just look at this equation, there are no colour changes or state changes or anything else in my reactants or products. So HBr will just dissolve in the aqueous solution. The halogenoalkane will perhaps just disappear because it's quite an oily substance, but that's about it. So it's just straightforward. This is the only real reaction that we know of halogenoalkanes. So don't panic about the circumstances being different or making it sound like there's other things added. Just go back to what reactions do halogenoalkanes do. This is the reaction that they do. So part II says write an ionic equation for the reaction that results in the formation of the precipitate, and we're given a clue, it's a cream precipitate. We shouldn't need that clue because the idea is the reaction forms HBr. HBr will dissolve in water and it's an aqueous solution to make bromide ions. So the ionic equation is going to be the same for all of the formations of silver halides. You just need to know this ionic equation confidently. Silver ion is Ag+, we just need to learn that, can't work it out from the periodic table. Bromide ion is Br-, AgBr is the precipitate, and we need a solid. So it's 1 mark for the correct formulae, there's no balancing required, and it's 1 mark for the state symbols, aqueous plus aqueous makes solid. Always worthwhile writing some sort of ionic equation, even if you might get stuck on the charges or something else might go wrong, simply because it's so easy to get the state symbol marks for a precipitation reaction because they're the same every time. And then the last part of this question is asking for the mechanism, including relevant dipoles, curly arrows and charges. So we can, I've had it drawn for us, you could have drawn it out again, that would be fine. Relevant dipoles means this one here, so it means the carbon-bromine bond. You can draw dipoles on the water molecule as well, but they're not really essential to it being a nucleophile. What's essential to the water being a nucleophile is to have a lone pair. That's optional, doesn't say about drawing lone pairs, but it is good practice to do that. So the curly arrows involved in the first step are going to be from the oxygen to the carbon. I'm just going underneath so I don't cross over the delta plus because it's a bit tricky otherwise. And then going from the middle of the bond to the bromine to break that bromine off. So the intermediate, there's a box here which suggests we need to draw something as an intermediate because then there's another arrow, and the reason for that is because we're adding water, not hydroxide, which is also a clue to our balanced equation. If we've done hydroxide ions, this should be a clue that we shouldn't be using hydroxide as the nucleophile. So we've got this idea where water has joined on and bromine has left as a Br- ion, and then because bromine has left as a Br-, that means we've got a plus left. So the charge where it says relevant charges, I put a plus there. If you want to put a Br- somewhere, that's fine. You could put it coming off here. Sometimes that's one way that people indicate something that's kind of left and isn't important anymore. If you want to include it in the next step of the mechanism, you can. That's kind of optional. So the most important thing in the next step is that we need a curly arrow from one of the hydrogens, doesn't matter which one, on the oxygen to go back to the oxygen to regain the lone pair that it donated to the carbon, and that means the hydrogen is being lost as H+, so the oxygen loses its positive charge and the hydrogen becomes a positive ion. So where are we getting the marks for this? The final mark is going to be for just drawing the final structure, which I'm going to run out of space for, so I'll just pop it down here, OH. Because it's a mechanism and it's not asked fully for a displayed formula, it's okay if you've got the bond between the O and the H. It's good practice to remember it's there. So that would be one mark. We would have one mark for my arrows, one mark for my dipole in the first step, so 2 marks for the first step, and then the third mark is for having both the charge and the curly arrow in the intermediate part. So that's how we get our 4 marks. So just a reason for adding ethanol. So we've drawn the reaction. Ethanol's not involved. This is a hydrolysis. This is reaction water substituting for the bromine. And it's not involved in observing the products because the product that we see is the silver bromide precipitate because of the silver nitrate. So the only reason for adding ethanol is as a solvent. So halogenoalkanes are quite non-polar molecules. Bit of a dipole, but there's not a huge difference between carbon and bromine. Enough for nucleophilic substitution, not really enough, doesn't have any strong interactions with water, and water is the reagent here, so we want the halogenoalkane to mix with water. So what ethanol does is simply help the halogenoalkane and the water to mix, because ethanol is hydrogen bonding at one end and non-polar hydrocarbon at the other end, so it's just a very good solvent. So you could simply just say as a solvent, or you could say to help the halogenoalkane or the haloalkane or the 2-bromopropane mix with water or with the aqueous part of the solution or something like that, just because otherwise it would probably sit at the bottom in a little puddle of oily liquid.